So welcome everybody, and welcome to my talk. It's a pleasure for me to meet you all here. And let's just start with my speech, exploring those prowess in immersive database development, immudb as a case study. So first of all, I'm Stefano Scafiti, lead software engineer at CodeNotary, and currently in charge for managing the immudb project, of which I'm going to talk to you about today. It's basically our open source database solution that has been written in Golang. And today I'm just going to tell you more about our experience with writing an high-performance application such as a database in Golang. And specifically, I'll focus on those features of Golang, of the language, that directed us to choose it for writing the project. We will explore how built-in support for Go routines and channels simplified the development. And also, we will focus later on some performance issues, mainly about the garbage collector. Finally, we will draw some conclusion on our discussion. So first of all, before diving into the details of Golang and immudb, let's just present what immudb is. So immudb is a tamper-proof ledger database solution, which also comes with built-in cryptographic proof and verification. That means that unlike other databases that only claim to be immutable just because they don't implement, for example, the delete statement and never physically erase your data, immudb also adds a layer of proof. That is to say, clients can convince themselves that the database has never been altered since the last time it was modified. It can operate in several modes. So at its heart, it's just a key value store as LevelDB or any other key value store can be. And it also builds a nice SQL abstraction on top of that, which comes with non-standard features. For example, the possibility to go back in time and query the history of your data, and also provide an additional simple JSON-style API. It shares several characteristics with blockchains, from which it inherits the cryptographic details, but also it's quite different at the core, being a centralized server and a database at its heart. And that's also why it can scale easily to handle millions of transactions per second, because of the fact that you don't have to run an additional consensus layer on top of the storage layer. And that's why it can scale to millions of transactions per second. So the project was started in 2020. About 70 contributors worked on it. We just released version 1.9.5, and the code base consists of about 146K lines of Golang-only code, which are enough to place it among medium-sized projects, and definitely worth for us to gather some valuable insights on it. So why is an immutable database important? For sure, the number of applications are countless, but everything where protecting your data is critical for the correct outcome of the system is definitely a right choice for a solution such as this. Just imagine for a second to build an online voting system. And I mean, you probably don't want Donald Trump to win the election just because your data has been tampered. How immutability is achieved at the core. So by leveraging two kind of core data structure, with the first one being the immutable append-only log, that is to say, quite a simple data structure. It's just a file which is managed in an append-only fashion. That is to say, random writes never happen, and entities are never modified in place, and regardless of whether we are talking about internal core data structure or just entities, raw documents, or wherever. And this also has a nice benefit in terms of performance, because we all know that today's SSD are heavily optimized for this kind of access pattern and perform better when you just write something to the end of a file. The other critical data structure is the Merkle tree, which is very useful when we talk about the cryptographic capabilities of the database. So on an high-level perspective, a Merkle tree is just a binary tree where each leaf node maps to an hash of a specific piece of content, in our case, transaction. And each internal node is just built recursively by sub-aggregating the hashes of the leaf nodes. So in immudb, the Merkle tree is constructed on top of the main ledger, the one which accepts the transactions. And it's also updated on the fly. That is to say, as new transaction come, we append, we compute changes, and we propagate all the new nodes up to the root in order to keep the tree balanced as well. Why is it useful for proving immutability? Well, because it enables us to compute two kinds of proof. The first one is the inclusion proof that shows that a specific piece of content really belongs to the Merkle tree root. In this case, for example, just imagine to prove that HC belongs to the root. You just have to forward the minimum number of nodes from the leaf to, in the path from the leaf to the root node to be able to reconstruct the root hash. And in this case, they are just HAB and HD. The second kind of proof is the consistency proof, which is useful given a source hash and a destination hash to be able to check that the destination hash is consistent with the old one. That is to say, the new tree is actually an extension of the old one. And that is done by transferring all the roots of the complete subtrees that have been handed in between. So since the source hash has been seen. And in these examples, we can see that you just have to forward three roots, which are the one colored red. So how can the client finally get a proof of immutability? We have to say that each client also caches the latest hash that it has seen for any database it is interacting with the server. And whenever it tries to fetch or set a new key, what it does is that it also requests this couple of proofs. So a consistency proof between the state that it caches and the latest one that the server claims to be legitimate, and an inclusion proof proving that the data it is getting really belongs to this state. And this is enough to prove immutability. So with this information in mind, with these requirements, it's now more easily to explore why Golang may have been the right choice for immudb. I know we might have gone for more common alternatives, for example, C or C++. We all know that they provide kind of consistent, close to the metal performance, and also the possibility to release memory manually at predictable points is really great when dealing with high-performance application. But also, they come with a steeper learning and learning curve, and also the fact of having to worry about explicit management of memory comes with additional complexity, and also it's quite error-prone because you can mess up with pointers at some point. You risk to double free a pointer or maybe reference memory that has never been allocated to your application. Another common alternative here is Java, but we found out that the additional overhead introduced by the JVM and also the fact of shipping it with the virtual machine really was not something we liked. So we knew that everything we were going to build was going to also make extensive use of cryptographic built-in primitives, and Golang has a quite robust offering in terms of that. Being a database, of course, we couldn't avoid to notice that Go routines and channels and everything which was built in the language would make our life easier in scaling in performance critical sections. And also we had several quite successful examples of adoption in larger code bases such as CockroachDB or BadgerDB, which are well-known and established databases written in Golang. Moreover, when talking about the garbage collection, Golang also provides you some way to put some pressure off of it. And we will explore later in this talk some of them, such as sync.pool, the use of the unsafe package, and so on. So regarding the first point, the one about the rich support for cryptographic primitive, I believe that showing the snippet really talks on its own. So this is actually our implementation of the in-memory Merkle tree, the one that we compute on top of a transaction and then that gets pushed to the disk later. And not only we can see that computing hashes in Golang is as easy as just calling a function, but also there are a couple of things such as the implicit manipulation of byte slices, the copy function, which really helps reducing a lot the amount of boilerplate code that we write. And of course, we could achieve a similar result with Java or C++, but for example, if we focus on Java, just to retrieve the instance of the hash function, you have to possibly handle an additional exception because getting an instance of the hash function can cause no such algorithm exception. And also, you don't have the subslicing operation built in the syntax, so you may have to use a byte buffer. And of course, the result would probably be twice the lines of code that we're seeing here, which is not so much. But still, if we imagine to propagate this to the whole code base, then the result, the difference starts to become sensitive. So the other reason we decided to go for Golang is that we definitely knew coroutines would make our life easier when scaling with the number of code. I believe that what you're thinking is that in any other language, we couldn't afford spawning an OS level thread in such a careless style. And we all know that that is due to the fact that threads living in the domain of the operating systems also introduce different performance costs in terms of context switching, so passing the context to the kernel, and also in terms of memory overheads. For example, if you consider Java, its stack is fixed size, and it's about 1 megabyte. In constant, as it happens with Golang, spawning a routine takes only time in the order of nanoseconds, and it also has a dynamically shrinking stack, which make it quite suitable to also use this kind of pattern in performance critical snippets. So, for example, if you look at this one, this is taken from the set of procedures which are responsible for committing a transaction to the disk. And what we are doing here is that we are trying to run in parallel the fact of serializing transaction and appending them to the disk with a CPU-bound operation, which is the Merkle tree construction that we just saw before. And we see how the channels, the use of channels also simplify not only fetching the result of the inner coroutine, but also joining and waiting for it to finish. So channels are a tool for enabling thread-safe communication between coroutines. But you also have to be careful about using them, because you may incur in unintentional deadlocks if you have a kind of circular access pattern when you propagate the ownership of your data. And this is why some usually say that you always have to prefer, for example, murex and a condition variable to a channel. But today, I want to show you an example where using channels in immudb made our life a little bit easier. So I'm going to introduce you the watcher sub primitive. On an high-level perspective, it's quite simple. It's just a monotonically increasing counter. So it can be just summarized as a counter whose state is represented by value. But it also provides the two additional operations. So a wait for method, which takes a context object and a specific value v. And basically, this method is for waiting for the counter to reach the desired value. So let's say it's 10, and we want to wait for it to reach the value 100 before we continue in our process. And the other one is the advanced method, which basically just increases the value of the counter. So this is quite useful inside the immudb. We make extensive use of this primitive. Just imagine, for example, a request that may want to wait for data to be fully durable on disk, or maybe because of the fact that the indexing happens in the background, you may want to wait for the transaction to be also indexed in order to query it after storing some data. So how did we use channel here? So a watcher's hub, it's just a map, and apart from the value. So this map associates to each possible value that you may want to wait for a wait point object, which is just a wrapper over a channel and some couple of fields more that are not useful actually for our purposes. And what we do in the wait for method is that firstly we just check that the value is already greater than or equal to the one we're trying to wait for. If so, we immediately exit. Otherwise, we retrieve the wait point object associated with the value. We initialize it if it was not. And then we finally block on the select statement, which can awake into conditions. So either the context is cancelled because of explicit cancellation or a timeout happening, or because the channel associated to the wait point got some signal. And that can happen in two cases. So either a value is received or the channel is closed. And actually, the fact of closing a channel is quite useful here, because without forwarding any value, so without adding any additional overhead on that, we can get all the coroutines to wake up at once. And also, each new coroutine trying to wait concurrently on the channel, once it's closed, it immediately awakes. So the advanced method is basically just looping across the value, the ones between our counter value and the one we are trying to advance it to, and just closes the associated channels to the wait point. Of course, we could have done this by using mutexes and condition variables, but the overhead in terms of complexity would be quite higher than this, and also not only you would have to declare two entities, so the mutex and the condition variable. Also pay attention to not using values in the map, because mutexes are labeled with the no-lock directive. But also, it wouldn't be clear how to seamlessly integrate this with the select statement. For example, for sure we would have to spawn an additional Go routine at each wait for invocation, just for synchronizing with the context. So when writing high-performance application, of course, the garbage collector really plays an important role. Maybe at early steps of development, you may want to not worry about it and just allocate memory when you need it. But later, when you also have to think about performance, it becomes very useful to kind of know some tricks to put some effort off of it. And today, I will explore some of this. One is the usage of sync.pool, which some of you may know, to reduce the number of total allocation. And the other one is are preferring values types to pointers when it is possible, and avoiding unnecessary copying by using the unsafe package. So first of all, let's just recap how the garbage collector works in Golang. So it basically uses a mark and sweep algorithm. That means that the process of reclaiming memory to the OS is split in two phases, which are mark and sweep. In the first phase, the garbage collector just navigates the whole program object graphs and tries to identify those objects, those references which are no more reachable. So in this example, you see that the one colored green are reachable by starting from program roots, and the one colored blue are dead object. And it's the job of this sweep phase to finally reclaim memory and free these objects. So just by knowing that, we can understand how the GC post time is not affected by the total number of bytes that we allocate, but rather by the amount of objects that live on the heap at a specific time. And this can help us to think to some optimizations for our application. So the first one is, of course, to just try to reduce the number of allocation that we do. So for example, there are scenarios where objects get allocated frequently, they are short-lived, and we just reset, they just go out of scope quite fast. That's where we can use what sync.pool offers us. That is to say, the ability of using a pool which just consists in a put and get method to easily recycle objects that get allocated frequently. So in this example, as we can see, we use it inside immudb to just avoiding allocating too much rows object and the connected buffers in query in RED heavy intensive workloads. And what the pool just takes is a new function that it calls whenever it has to allocate a new object. And also, when finally releasing an object, we just have to implement a sort of reset logic to maybe unset some attribute that may be dirty by its usage. The other tip is to prefer values to pointer when possible. So people that come from C and C++ usually tend to use pointers and to prefer them to values. But when doing that, you have to think about the fact that if you then allocate, in this example, an object of type myStruct on the left, then you also have to allocate explicitly each of its fields, because they also take a reference to the values. On the right, we just allocate a myStruct object, and we get all the field allocated in a wall. And this is quite beneficial for the garbage collector, because it just sees a reference instead of 3. To explore more this concept, I just put here this simple snippet which comes from our cache implementation. So it simply consists of a put and get method, and it just maps key and value byte slices. It's just a quite trivial implementation of this could be just keeping a map which just associates the key to the value directly to the slices. But actually, for the reason that I said, this is not quite beneficial for the garbage collector, because it has to navigate an object for each value. So instead, what we do is that we just allocate a large buffer, which is large enough to hold all the object in the cache that we need, depending on a predefined size. And then we only store the pointers to the starting location within this buffer on the entries that we then have to serialize. So this way we avoid to keep a pointer type in the map, and we definitely write more efficient code, but also more error-prone code, because we need to handle carefully the serialization. This directly leads us to the next point, the one about unsafe operations. So as you may have seen, the map key type is a string, because of the fact that we cannot put directly byte slice there. And what we can do to avoid extra copying is to use the unsafe operation to extract the reference to a slice and convert it to a string. But when you use unsafe, you also have to care about the lifetime of the memory you are referencing, because then the pointer that you get is not checked by the garbage collector. And what happens is that if your memory gets cleared in the meantime, then you may just have a sudden panic or undefined behavior in your application. So this concludes our discussion about immudb and GoLang. I hope that with this talk, I just left the impression that GoLang is a right fit for writing high-performance application, not only because of its nice features in terms of concurrency and ease static compilation and whatever we can think about, but also because thinking in a performance-oriented way, we also have several tools that the language provides us for freeing, for making the life easier to the garbage collector. And projects like immudb showcase that. So you find some useful pointers here. So you find the repository of immudb in GitHub. Of course, it's publicly accessible. You also find links to the documentation and to our website. And if you are interested, we're also hiring. Thank you for the attention.
Okay, thank you for your talk. Are there any questions? Don't be shy. Okay.
Yeah, thank you for the talk. I saw that you have a lot of ways of mitigating the garbage collection pressure. but still the garbage collector is still there. Is something that you are missing or something that you are not, you are hitting your face in the wall with that right now about the garbage collection? And
to further mitigate, you mean?
yeah, no, you have mitigated a lot, but the garbage collector is still there. So
yeah,
it's getting in the way of immutable or
yeah, I mean, of course, the garbage collector is not something that you can completely remove when you write an high-performance application in GoLab, and that's why I was talking about reducing the pressure. So what you can do in the worst case, and what some developers even, for example, just take BudgerDB as an example. I don't know if you ever used it, but what the developer did at some point, they switched to manual memory management. So if managing memory and the impact of the garbage collector is prohibitive at some point, you may have to manage memory explicitly. But in the meantime, you go there step by step. I mean, you don't just decide to switch to manual memory management from in a couple of minutes. Firstly, maybe you want to see what you can gain with what the language provides.
Great, thank you.
Thank you for your talk. Among all these optimization techniques, is there one that stood out in terms of giving the most benefits?
Yes.
Just from your experience with your project?
Yes, for sure. The second one, the one about preferring values to pointer, because as I said, it directly impacts to the number of objects that have to be checked. So we made extensive use of this concept. So for example, when implementing B-trees, something that you may do is that you just allocate nodes. But actually, an efficient way to do that is to represent the nodes as pages. And then you can apply a similar technique to the one I've shown before. That is to say, you pre-allocate buffers large enough to hold the full set of pages in memory. And then you just try to keep references to these. You leverage the use of unsafe operation for performing conversion and avoid allocating object. And yeah, you can get quite some benefit from this.
Thank you.
Any other question? Yep.
Hi, thanks for your talk. There is one thing that I didn't quite get. Were you suggesting with unsafe conversion that it is beneficial from a performance perspective to do it and then eventually recover from a panic if it happens?
No, I mean, I didn't mean that you recover from panic. I mean that when you use unsafe, you have to make sure that the memory that the reference you get is pointing to lives for all the time that you deal with this pointer. So, for example, just imagine in this case you extract the unsafe pointer and you get a string reference to the buffer. But then in the meantime, the buffer goes out of scope and then it's cleared by the garbage collector. So what's happening is that the string internal pointer are still pointing to some memory that has been freed in the meantime, but you may try to access them. So this is something that you definitely have to avoid. So for example, in this case, if we use this concept here, we have to guarantee that the keys that we store in the map and that we get through the unsafe operation lives for all the time that we use the cache. And that is true because we pre-allocate the buffer, and it's something that always lives inside the application for the whole lifetime of the application.
Clear, thanks.
Any other question? Okay, that's it.
Thank you.